Okay. So we want to talk about today about order of elements in a group. Okay, so what is the definition of an order in a group? Okay, just a minute. Okay. First, we're gonna define the order of the whole group, and then the order of an element in the group. Okay, so given a group G, its order is its cardinality. I mean, the number of elements. I mean, this can be also, of course, infinite. Yes, we denoted by this. Okay, this is not absolute value. This is the number of element G.
So it must be a group, not a general algebraic structure.
There is no such meaning. I mean, of course, there is a meaning, but we are going to concentrate now in groups.
Sure, thanks.
I don't think that we call it order if it's not a group. We just call it cardinality, I think. Okay, given an element, or let's write it, the order of G inside G is, we write it O of G. This is the order of G. Okay, is the minimal natural number such that G in the power of K is the neutral. Okay, so it's the minimal power under which you get back to the identity. And we write it infinity if there is no such K. Okay. And this is very important. We are going to use it many times. So let us see examples. Say if G is Z6. Okay, so if I'm writing just Z6, I mean with the operation of plus modulo 6. Okay.
Yeah, I just said that RL asked a question in the chat.
Mm-hmm. Sorry, what is the question?
RL asked
Sorry, I didn't see it. No, No. It doesn't have to be cyclic. Thank you. No, it's not. It doesn't have to be cyclic. Okay. So this example it is cyclic, but it doesn't have to be cyclic, of course. If G is okay, so inside this group, what is the order of 1? Is 6. Okay, because 1 is a generator. So the only time, the minimal time you get back to 0 is after 6 times. Because you know the power of 6 is 1 plus 1 plus 1 6 times. So this is our E. But the order of 2 is 3. Okay. You want something not cyclic, for example. Okay. Does the piano annoy you? No? Yes? No?
What piano?
If yes, please let me know. Okay, so there are 4 elements in this group. Of course, this group is not cyclic. Okay, there is no generator here. So to any element here, except of D here, okay, so to any element not E in G, the order of G is 2, right? Of course, always the order of E is 1. This is always true. In G equals to Z, okay, any element besides 0 is of infinite order. Because you do not get back to 0. There is now a torsion, a loop. Let us see last example. U10. Okay. So of course, the order of 1 is 1. The order of 3, what is, by the way, it's always true that the order of an element, okay, claim. This is an obvious claim. The order of an element is always the order of the group it generates. Because this is the number of distinct powers until the loop. I mean, until it gets back to an entity. I mean, it is just exactly the order of 1. This is G0 and G and G2 until G order of G minus 1. So this is always true. Okay, this is always true. So here, for example, if we take 3, we get 1, 3, 9, and 7. So the order of 3 is 4. And the order of 9 is 2. Now, pay attention that always the order of an element divides the order of the group. It must be. We're going to talk about later. But you see, always, I mean, it cannot be free. Okay? It must divide the order of the group. Okay. It's like you take the old group and you shift the elements that being generated by this element. So you get a number, an integral number of shifts. Okay, so okay, we are going to talk about. Is there any question until now? Okay. So I claim the following things. If the order of an element A divides the number k, this is if and only if A in the power of k is E. So let us prove it. One direction is trivial. I mean, if OA divides k, so of course A in the power of k is E. Why? Okay, so let us prove this direction. Because what does it mean to divide k? If OA divides k, this means that there exists some integral quotient Q such that k is OA multiplied by Q. So what is AK? AK is A OAQ, and we can write it in this way. Now, this is E, because always the order gets you back to E. Okay, and E in the power of Q is E. E remains E. So this is the trivial direction. On the other direction, okay, if AK equals to E, okay, so of course, if of course, let us write then. Then, by definition, the order of A is less or equal to K, because by definition, OA is the minimal power that makes it. So of course, OA is less or equal to K by definition of an order. So we can think about the decomposition. K is OA times Q plus R, when R is less than OA. Okay? I mean, we take the maximal times of OA inside K. And then we get that A time K, it is given to be E, but we can write it also in this way. Sorry. Okay, because this is K, but this is E. So we get AR equal to E, and this is a contradiction because OA should have been the minimal unless R is 0. Okay, because if not, you get a less number which takes you back to E. By the way, it doesn't matter if it's a plus R or minus R. Okay, I will shortly talk about. Okay, so this means that OA actually divides K because there is no residue. Okay, so by the way, I will write it as a remark. Of course, always OG equals to O, the inverse of G. I mean, always the order of an element equals to the order of its inverse. Why is it true? Because this is the cardinality of the group being generated by G. But this is exactly the same set being generated by its inverse, because anyway, you take any integral power, negative, positive. So of course, this is the same thing. Okay, so this is the same set. Okay. By the way, okay. So we can deduce that if F from G to H is homomorphism, okay, I remind you, homomorphism, it means that it preserves the action, the operation. Okay, then the order of let's write it like this. To any element A in G, the order of the image inside H, okay, divides the order of A. I mean, if you take A from G to H, be sure that the order here divides the original order of A. Okay, why is it true? Because how do you show that? By the previous claim, you only need to show, okay, you only need to show that A in the power of I mean, you want to show, okay, that this happens. Okay, but we know that FA in the power of OA, okay, FA in the power of OA, what is it? Okay, it's just OA times FA. but it is on a homomorphism. So FA OA times, it's like FA in the power of A. Because it's homomorphism. So it is F of E of G. And we have already shown that in groups or in monoid in general, F of EG is EH. So what? So if this in the power of A is EH, then it means that the real order of FA divides OA. Because if this takes it to EH, okay, so the real order should divide it, okay, by the last claim. By the way, the order of the image could be 1. I mean, you can take the trivial homomorphism that takes everything to 1. It's not so interesting, but it's possible. So this can be very, small. Okay? You can lose everything by sending everything to E. But if you have an order of the image, okay, it must divide the original order of A. Okay, we're going to see an example later. Let us concentrate now in cyclic groups. Okay. So you know a cyclic group is being generated by one element.
Generators.
Sorry?
Generators.
Yes, I mean, there exists at least one element that can generate itself by its powers, the all elements. I mean, so now we're gonna see that actually, it's very, it makes sense, okay, to say that you have up to isomorphism only one infinite cyclic group. For example, you can take Z, because the table is going to be very, very simple. I mean, you have 1, 2, 3, or in other words, A square, A in the third, and etc. And similarly, you have only one cyclic group up to isomorphism of a given order. Okay, so before we show that, let us write a remark. Homomorphic image. I mean, the image of homomorphism of a cyclic group is a cyclic group. Why is it true? Because if you have an homomorphism from G to H, and G is cyclic, okay, so what is the image of F? The image of F is being generated by the image of G, because everything here is subpower of G. So you only should take care of the image of one G. I mean, it's homomorphism. I mean, GK, the F of GK, of course, is FGK. Okay, it's homomorphism. So the image of A is being generated by the image of the generator. So it's cyclic. Okay, so it is cyclic also. I mean, an homomorphic image of a cyclic group must be also cyclic. I mean, of course, H should not be cyclic. I mean, maybe the image is very small inside H. We don't know. Okay. And now we can talk about the theorem I mentioned. Which says the following.
Just to be sure, so there is a subgroup in H which is cyclic.
Yes,
right?
Exactly. I mean, we didn't show that yet, but any image, any homomorphic image is a subgroup in the target.
Right. Okay.
And the kernel is always a subgroup in the source.
So what do you mean by when you said the kernel?
Everything that goes by F to the to E.
To E, right. Okay.
We didn't define it yet, but
yeah, linear algebra kernel.
From linear algebra.
Yeah. Okay.
Okay,
yeah.
This is the kernel.
There are a lot of kernels in mathematics, so yeah. Okay.
Yes. Okay. Okay. So the theorem says the following. This is called sometimes classification of cyclic groups. So what does it say? It says that let G be a cyclic group. Then if G is infinite, then it must be isomorphic to Z. This is the canonical representative of the infinite cyclic groups. Okay. And if G is of order n, the G is isomorphic to Zn. I mean, you know what mathematicians do. I mean, they classify. Okay, they classify object. I mean, when a mathematician see an object, he says, we know this category of objects. Okay, so we know the properties are the same and etc. So for us, I mean, there is only one group, cyclic group of order n. The other examples are just, I mean, like you say, dresses. I mean, another dress. Okay. 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 So how do we show that? That's a proof. So in order to show isomorphism, you should show a map which is both injective and surjective. That is an homomorphism. So in A, we are going to define, okay, a set F going from Z to G. We don't know what G is. We only know it is cyclic and it is being generated by some element A. Okay, so the thing is, we define it in this way: to any integral number k from Z, we send it to A in the power of k. That's all. So let us see it is homomorphism. F of k plus m is by definition ak plus m, which is akam. I don't know what the operation here is, doesn't matter. Okay, which is fk fm. Okay, now of course it is injective and subjective. Okay, because you can produce any element here. I mean, because you can have any power, any integral power, so you can cover all G. Okay, in G. So F is subjective, and of course, once you know what is AK, then you know what is K. Okay, why is it true? Why is it true? Okay, that it is injective. I mean, why it is injective? Why is it? I mean, we want to show that if two images are the same, so the sources, I mean, must be the same. Okay? Or in the opposite way, I mean, if you have two different sources, you must have two different images. So to any m which differs from k, okay, we claim that am is different than ak. Why? Otherwise, we could have deduced, okay, suppose I mean, suppose k is greater than m, okay, then we can multiply both sides. I mean, everything is invertible, so we can both side multiply by a k minus m. I mean, we can both multiply a minus m here. So in here you get e, which is equal to a k minus m. But the order of a is infinite. So the only m that makes it, okay, is what is, okay. I mean, we can write it like this. I mean, if we don't need all this, okay, if this is better, you write it in this way, okay. If ak equals to am, okay, then, okay, this is better. Suppose K is greater or equal to M. So E should be K minus N. So you can deduce from here, okay, but the order of A is infinite. Of course, it is given. So what can we deduce? That K equal to M, okay? So it is both injective and surjective and homomorphism. So it is an isomorphism, okay. B is similar. Okay, we set again F from Z then to G by taking, okay, now it's a little bit different. Okay, we take again a K to be a K. Okay, it's the same thing for now. So why is it homomorphism? Let us check it. F, now you know the operation here is not just plus like it was here. It is plus modulo N. So K plus, okay, this is modulo N. Okay. So what is K plus M modulo N? This is or K plus M or K plus M plus I mean, if we remove it can be also this one. I mean, there is a chance that K plus M exceeds N. Okay, so in this case, okay, if K plus M is less than N, then this is the same thing. But if K plus M, and it's possible, it exceeds N, then it cannot have 2 times N, okay? So this plus, which is modulo N, is just taking K plus M minus N. So this is the same thing as the residue. Is it clear?
Yeah, but it doesn't have to be -1, and it should be minus some scalar times N, no? Because
because we have initially taken here the residue and here the residue. So you cannot have more than 1 times N.
Okay.
I mean, you cannot have more than 1 time N here, and I mean, see, it's least N, okay? So what is F? So it is A K plus M minus alpha N, where alpha is 0 or 1. Anyway, I mean, even if it were a Q here, I mean, okay. Now I claim that this is E. Why is it E? Okay, why is it E? Because it is given that the order of G is N in B. And we have already seen, okay, that Oh, we didn't see that? Didn't see that. That always, we didn't see that. We didn't see that. We have said it, but we didn't say show that. Okay, we didn't show that yet. Okay, we didn't show that always the order of an element divides the order of the group. Okay, so we're going to show that. Okay, later. Okay. Okay, we didn't show that yet. So now you have to believe me, okay, that this whole thing is E. So it is homomorphism. So now I color it in let us say, okay, we have to show that. We're going, it will be a direct, I mean, from a Lagrange theorem, that always an order of an element divides the order of the group. Okay, so it's homomorphism. Why is it now? Since now both sets are finite, so it's equivalent to show surjectivity or injectivity is the same thing. Okay, because it's finite sets. Okay, so of course it's subjective. Okay. Okay. Any power. Okay. Any integral power. K from 0 to n minus 1 exist in Z so F is subjective because you know the target is the power of A. Okay, thus also injective is the finite set. Okay, so up to isomorphism, we have only one cyclic group to a given order. Okay, I repeat, up to isomorphism, we have only one group of a given order. Let us think of examples. Take, for example, okay, first, of course, Z is isomorphic to 2Z. Though this is embedded inside Z. I mean, here you have only even numbers, and here you have more. You have also the odds, but they are isomorphic. Okay, what can be the isomorphism? What do you say? F of K is 2K. Okay. This is both subjective, injective, and homomorphism. Okay. And I wrote here 2, but I could have written any number, 3, 4, 5, 6. Okay. I mean, once it is cyclic and infinite, it is homomorphic to Z.
Yeah, I have a question.
Yes.
Why does it have to be Z? when we talked about cyclic groups, we didn't mention that I don't know how to call it, the field must be Z.
You are asking now not a mathematical question, but more, I don't know. I mean, you asking me, why do we choose Z to be the representative of the cyclist group, of this infinite cyclic group? This is your question, isn't it?
Sort of. When you, my question, I think it's simpler. Can it be, I don't know, the rational?
No, the rational is far from being cyclic. Of course. This is exactly Z. I mean, Z is exactly the basic additive group. Okay, that you add things. Okay. I mean, every abelian group, the initial object is Z, because you just add things. Q is far from being cyclic. It's even of infinitely rank, not only infinite now. Okay.
Okay, thanks.
You need, I mean, infinitely primes to generate all the rationals. But Z, you need only one, that's all. I mean, you can create everything by just one. So this is the initial object in algebra, okay? This is I mean, all algebra is based on Z. So this is the most, I mean, you cannot read any article in algebra without seeing Z. I mean, okay?
Yeah, thanks.
Okay. For example, if I take all the complex number that being generated by powers of this complex number. This is a subgroup of the complex, I mean, which is actually C without zero with multiplication, okay? So this is, I mean, you take this number, this complex number, and you take powers of it. You get cyclic group, of course. Is this group is finite or infinite? The answer is infinite. Why? How do I know that this group is infinite? Because this can be written as root of 2 e I power of 4, isn't it? Do you agree? You agree? This is the polar representation of this number. So of course, if we take, or if you want, if you prefer, you can write it like this. So any power of this thing, okay, this will never be 1. Never. Because the radius is exceeds or going, I mean, it cannot back be 1 to any n. Okay? Because it is actually equal to So this can be 1, of course, but this could not be 1. Okay, unless n is 0. Okay, so this is infinite. So if it's infinite, I can deduce that it is isomorphic to Z. Okay? And it's very simple to find the isomorphism. Take the generator of Z to the generator of the other group, or in other words, Fk will be the power of K. That's all. More generally, we can say the following thing. Take some complex number. Okay, so take some complex number, which is not 0. And take by multiplication all the power of Z. This will be a finite group if and only if you need 2 conditions. You need 2 conditions. What do you think will be the conditions in order that this group will be finite? Let us write Z as REI theta. What are the 2 conditions under which this will be finite?
R equals to 0, maybe?
No, R equals to 1.
Right, yeah.
If it's 0, so the number is 0. Okay, so actually we are on the unit cycle. I mean, we have only EI theta. This is the first condition, but it's not enough because we can turn around infinite times and never go back to 1. We can do that. So how do we guarantee that we go back to 1 in some power? Okay, for example, here we have Z. How can we be
So
sure?
pi should be between 0 and 2 pi. Theta.
Okay,
should
so
be-
let me write what you say. Okay, the ratio between theta and pi should be rational number. If it's so, I mean, okay, if is, for example, A divided by B, then EI theta in the power of, say, 2B, this is a natural number or integral number. Okay, so this will be E I of, instead of theta, I write A by B to B, and this is E1. Okay, so these are the 2 conditions. I once heard, flowers, I don't know how do you say it in English, ale koteret. I mean,
I
they
think
have,
it's petal, something like that.
okay, So they want to preserve the water of the rain. So they are put in by nature in some angle that you don't have. I mean, if you finish if you are doing the whole cycle, you don't get back to the same position, so you don't have a possibility for the rain to go down. I mean, you always have a lower I forgot my English today. Okay, you don't have one leaf below another. Okay, you always have some cover. Okay, so nature has done this. I mean, it's exactly what we are doing here. I mean, if this theta is not does not satisfy this, then we can turn out forever and never get back to one, never. Okay, so it must be something like pi, this theta. Okay. Another thing we want to see, we're gonna see how all this thing has to do with cryptography. We just need the patience. Okay. So Jerome, to any two natural number, okay, Zn direct product with Zm is isomorphic to Znm, okay, if and only if N and M are core primes. Now we have seen this direction from right to left. You remember we have proved it by the Chinese remainder theorem. This is what you said, Erel. Okay, that if we have this, okay, so we can find, I mean, it's even isomorphism of rings. I mean, we for both plus and multiplication, that any element here, we can think about modulo n psic modulo m, and this f will be both injective and surjective and and homomorphism. So we have seen this direction. So this direction for the other one, what do we need to show? That if this is true, which means, in other words, because anyway, both sides here have NM elements, because this is our pairs of number. So of course you have NM pairs here, and the same elements, this is the same number of elements, always. Doesn't depend on this condition. But what do we mean isomorphism? When I say that this group is isomorphic to Znm, in other words, I mean that this group of Nm elements is cyclic, because of course this is cyclic. Okay? And we have already said that you have only one up to isomorphism cyclic group given an order. So if we know that this order is NM, and we do know that, okay, to show that this is, and we know that it is homomorphic to ZNM, okay, so we actually know that this is cyclic, okay? So from this to this, we know that Zn times Zm is cyclic, okay? We know that. Okay, so let us write it, okay? We are given that Zn is cyclic. Why is it cyclic? Because it is homomorphic to a cyclic group. Okay, so any element, any group that is homomorphic to a cyclic group is cyclic. Okay, in other words, there exists some element in Zn, Zm, such that it generates the whole group. Or in other words, the order of this element, what is the order of this element is? If we know it is cyclic, it means that there is an element, at least one, that is order is what is?
N times M.
Yes. I mean, it doesn't go back to 0, 0 before he has covered all NM elements here. Okay. Now we want to show that this implies that NM are co-prime. Okay. So let us take this generator and look at the power of the LCM. Okay, I remind you what LCM is. LCM is the least common multiplication. I mean, it's the least natural number being divided by both N and M. So it's greater than N and M. It's being divided by both. Okay, so what we get here, this power. When I say power in Z, I mean actually taking this number of times A and this number of times B. This is what I call power. I mean, you take this AB plus this time of times, okay? But this is, okay, some n Q1 because it's being divided by n. And similarly, we can call it n Q2. Okay, so what is this element? Remember that this belongs to Zn and this belongs to Zn. So what is this element? If you have n times something and m times something, which is integral, and you are living here, so what is this element?
An element in the group.
What is?
Some element in the group now.
0, 0.
So why?
Because it is n times something, and n times something here is 0.
Oh, okay, yeah.
Okay. So this is very strange, because apparently we have find an order, I mean a power which is less or equal to the real order of AB. Okay, we know that but we know that NM multiplied with NM is equal to, you remember, we have shown that? You remember? And this is the order of this element. Because it is a generator. Okay, so if this is the generator, this should be the minimal. And now we've seen that this also does the job. So what can we deduce? If this should be the minimal, but this already does the job, so what can we deduce? Okay, this should be less or equal to this, because this is the order. So if this take you to E, okay, if this take you to E, so this should be less or equal. So what does this have to do? Have to be? 1. Actually, they must be the same, because unless it is 1, okay, if it is not 1, then how can it be that something, suppose it is 2, okay, so this is NM divided by 2, so it's something smaller, but this take you to E, and this should be the minimal power that takes you to E. Okay. Okay. So we have seen in the past some okay, some other example. I mean, okay. Of course, this is not cyclic, or I don't know. Okay. Okay. This is if and only if. Okay. Do you have any question so far? You know, it's like playing Lego. I mean, you have parts and smaller parts, and the question what you can build from, you know, some parts, and what you cannot build. Okay. So okay. Another claim is the following. Let G be a group, some abstract group, and A inside G with order N, which is very general. then I claim that to any d smaller or equal to n, okay, the power of a, the order of a in power of d is equal to n divided by the GCD. Okay. Okay, of course, if d is 1, so you get back to OAN. But it's like the Lego that we have talking about. I mean, if you take two parts and you take them together, okay, so the order should be in general smaller, okay, like we've seen, okay, for example, the order of 1 in ZC is 6, okay, but the order of 2 is 3, okay. Why is it so? Because 2 is the power in 1 in the power of 2, so it's actually 6 divided by 2, 6, so it's okay. Okay, why is it true? Proof. So in order to show that some number is the order of some element, we need to show two things. First, that this element in the power of this given number is E. We call it feasibility. I mean, that it can be, it's possible. Okay, this is a possible number which can be the order. The next thing we should show that this is the minimal such. Okay, so let us check. A in the power of D in the power of n. So of course we can write it like this. By the way, I cannot write here anything. I mean, this is integral. Why is it integral? Because this is GCD. So this divides both D and N. So this is a natural number. So this is of course E. This is okay, so it's possible. The next thing we want to show is minimality. Okay. So suppose that you have some t such that you get to E. So we need to show what do we need to show? If any t takes this element to E, so we want to show what? I mean, our purpose is to show that this is the order of AD. Okay, so we want to show that n is less or equal to t. And then we can deduce that this is the minimal power. Okay, I mean, any t that will get you to E, it will be greater or equal. Okay, of course, this alone doesn't, it's not sufficient, because you have to show that it gets to E. But now we show the minimality. We have already shown the feasibility. Okay. I think here we miss some I. Okay. So how do we show that? Okay. We say that if this is true, then A dt is E. Okay. But, okay. But OA is, the order of A is N. So this power should divide N. We have seen it in the beginning of this lecture. Okay, so if you have some K that gets you to E, then the order, the opposite way, the order should divide dt. And from here, we can also deduce, okay, that if we divide both by the GCD, then it remains true. I mean, these are two numbers, both being divided by this number. So it remains true. But we also know okay, we know that N and this number are coprimes. How do I know that? How do I know that every time that I take any D, any N, this will be true? Because if it wasn't one, then there is, then would it would have some factor here that belongs both to N and D and do not belong to the GCD. But the GCD is the greatest common divisor. So once you divide both by this, you're left with one. I mean, they have no common divisor. I mean, once you divide it by Dn, okay? So if these are coprime, so, and you know that this divides this number, so this doesn't appear in this factor because they are coprime, okay? It must be an in T. Or in other words, T is less or equal. Oh, the opposite, greater or. Okay, this is what we wanted to show. Let us see how can we use this, this claim. Example. Suppose G is being generated by A, okay? is finite. Okay, in other words, what is the order of A? It's the order of G. Because A spans all the element of G. And I'm asking myself, what other elements here do the same job? I mean, all elements here are A in the power of some D. Okay? To what D AD is equal to G? This is my question. What do you say? I mean, of course, for D equal to 1, it is given. Okay? And I'm asking myself, to what D this will be still maybe another generator of G. What do you think? I mean, saying this is like saying that the order of AD is G. But we have seen that the order of AD, okay, the order of AD is the order of A divided by Dn. It's the order of A divided by so actually to any D that is co-prime to the order of G, we will get another generator. Okay? Of course, starting from let us see an example. Take U10. Okay? 3 is generator. What else? I mean, let us represent the elements of U10 by powers of 3. So this is 3, 0, 3, 1, 3, 4, and 3, 3, isn't it? Just let me check it. 3, no, here is 2, not 4. Here is 2, and this is 3. Okay? This is 3 in the power of 2. Okay? And 9 multiplied with 3 is 27. 27 modulo 10 is 7. So we know already that 3 is a generator. So what can be another generator? Now you have to answer me that. What can
5.
be,
For
what?
example, 5.
We don't have 5 here.
It must be in the group.
Yes, what other generator, other element beside of 3 spans the whole group? By the way, I remind you, and you can see it, that the order of U10 is 4. It's 4. So if 3 is the generator, what can be another generator? What can be another generator? Okay, if 3 is a generator, then we have said that any power of this generator such that this power is co-prime to the order of the group, there'll be another generator. So what can I take from here?
7.
7. Because, okay, because 3 is co-prime to 10. But this is not a generator because 2 is not a co-prime to 10. Okay. So this U10 can be also generated by 7. So corollary.
You meant 3 and 4 in the brackets.
Yes, sorry, thank you. Thank you very much. Of course, you are right. Thank you. Thank you. You know, mathematicians think one thing, write another thing, and spell a third thing. Okay, so, but you cannot do that. Thank you. Thank you. Okay. If the Euler group in general is cyclic, how many generators, how many elements can be each one alone a generator? Okay, suppose I don't know, UN is some G, okay? So we know that G2 until G what? Until G what? What can I write here? What is the last element?
O of G.
The order of the Euler group, I mean phi n, this is the Euler, minus 1. Because the next thing will be again E, because it's the order of the group. Okay. So how many elements here? I mean, think of the powers. How many elements here will be prime to phi n? How many elements here? Think of the powers only. Okay, will be prime to phi n. Okay, the answer is phi of phi n. For example, here, U10, phi of tens is 4, and the number of elements that can generate U10 is 2. Okay, these greens. Okay, these are generators. Is it clear what I've just said now? I mean, phi of n is the order of the group, UN, and the number of powers that are co-prime to this order are phi of phi n.
Can you please repeat the last sentence?
Yes, the number of elements in UN is phi n, because these are the invertible with respect to multiplication. And inside, once you spend the all powers, which is phi n numbers, the powers that are co-prime to phi n is phi of phi n. Because always phi is the number of primes until this number that are co-prime to this number. So the number of powers that co-prime to phi n is phi of phi n. Okay, for example, here, it was phi of phi 10. It was 2. Okay? So we can know how many elements can each one alone produce the whole group. My time is out. So if there is no question, I would like to thank you for listening.
Thank you.
Thank you.
Have a good weekend. There is a chat. I didn't see it. Thank you. Okay. Okay, bye.